Next, heat of hydration. Heat of hydration. So this heat of hydration, it is applicable only for the inorganic salts. So for example, we are dissolving copper sulfate into the water. So when we add the copper sulfate into the water, the copper sulfate will continuously dissolves. But during the dissolution, so many changes will take place. So in one of the earliest changes, what actually happens is, first if you add 1 mole of the copper sulfate into the water, this 1 mole of the copper sulfate will always combine with a definite number of moles of the water. That definite number is 5. 1 mole of the copper sulfate will combine with 5 moles of the water and it converts into copper sulfate 5H2O. That means pentahydrate. After converting into copper sulfate pentahydrate, the substance will remain in the same solid state. Therefore, in this entire process, you see the water molecules have been simply absorbed into the crystal lattice of the copper sulfate. Even after absorption of the water molecules, the substance is still in the solid state. Therefore, hydration. Hydration means absorption of the water into any crystal lattice is called hydration. Next, during this absorption of a definite number of moles of the water, always heat will be liberated. Hence, this heat of hydration, it is always exothermic. Always heat is liberated. Therefore, the heat of hydration means the quantity of heat liberated during the absorption of definite number of moles of the water into 1 mole of the ionic crystal lattice is called heat of hydration. It is always exothermic in nature. Next, heat of atomization. Heat of atomization. So first you observe this change. We are taking 1 mole of the ammonia. We are supplying sufficient amount of the heat energy. Therefore, here we are getting the independent atoms. All these atoms are in the gaseous state. Therefore, during heat of atomization, we will convert every type of the molecule into its constituent atoms. Therefore, the quantity of heat required to convert 1 mole of the molecules, quantity of heat required to convert 1 mole of the molecules into their constituent atoms is called heat of atomization. During heat of atomization, here compulsorily on the product side, we should get the atoms in the independent state. This side, the molecules can exist either in the gaseous state or liquid state or in some other state. For example, sodium, it is in the solid state. Here we have the sodium is in the gaseous state. This is called heat of atomization. Next, heat of sublimation. Heat of sublimation. So during sublimation, the substance will always convert from solid state to the gaseous state without passing through the liquid state. So the process of conversion of solid state into gaseous state without passing through liquid state is called sublimation. During the sublimation, always some amount of heat energy is required. Therefore, it is always endothermic. It is always endothermic. Next, see in this sublimation process, the substance is directly converting into the gaseous state. Heat of sublimation. Sublimation means the process of conversion of the solid into gaseous state without passing through liquid state is called sublimation. During the sublimation, always a definite amount of energy is absorbed. Hence, sublimation is endothermic. Next, during the conversion from solid state to gaseous state, sometimes the solid state can convert into the liquid state, then that liquid can convert into the gaseous state like this. For example, if you take the water, now water is in the solid state. If you supply some amount of the heat energy, it will go to the liquid state. Then again, if you supply some more amount of heat energy, then it will go to the vapor state. This conversion from solid state to liquid state is called fusion. The conversion from liquid to gaseous state is called vaporization. You see, in this second chain, Initially we have taken the solid, finally we got the gas. Here we have taken the solid, we got the gas. The difference between the two changes is, in a single step this solid has become gas. Here in two stages the solid has become gas. Therefore, here if some amount of energy is absorbed, here also same amount of energy must be absorbed. Therefore, the heat of sublimation is equal to heat of fusion plus heat of vaporization. Heat of vaporization. Next one. So let us observe this change. Ammonium chloride, on supplying a small amount of heat energy, the ammonium chloride will go to the vapor state. So since it is directly converting from solid to gas state, it can be called as the sublimation stage. Next, sodium. If you supply small amount of heat energy, the sodium can directly go to the gas state. Therefore, here also sublimation is taking place, here sublimation is taking place. But here during sublimation we are getting the independent atoms. Here during sublimation we are getting independent molecules. Hence, this sublimation can be also called as the atomization, but the sublimation is not called atomization. Therefore, here heat of sublimation and heat of atomization are same. Here heat of sublimation and heat of atomization are different. Next one. Heat of solution. Heat of solution. See, we have taken a very large amount of the water. Into this very large amount of the water, now we are adding 1 mole of the inorganic crystal lattice. Let us say we are adding 1 mole of the calcium chloride. So when 1 mole of the calcium chloride is added into a large quantity of the water, the calcium chloride will undergo dissolution. But that dissolution takes place in 2 stages. In the first stage, the calcium chloride crystal lattice will be broken into independent ions. That means soon after adding the calcium chloride crystal into the water, all the ionic bonds present between the constituent ions will be broken, hence independent ions will be formed. Therefore, first stage is the breakage of the lattice to produce the independent ions. For the breakage of the lattice, always a definite amount of energy is absorbed. How much energy is absorbed? Equivalent to lattice energy. Therefore, in the first stage, the enthalpy change is positive. Next, after the breakage of the lattice, after separation of the all ions, then the ions will start undergoing hydration. So during hydration, all ions, the ions will attract a definite number of solvent molecules around them. Then they form bond with those solvent molecules. Hence, always heat energy is released. The amount of the energy released in the second stage is represented as the hydration stage. Therefore, in the first stage, some amount of heat energy has been absorbed, that is equivalent to lattice energy. In the second stage, some amount of heat energy is released, that is equivalent to hydration energy. Therefore, the total energy change involved during the formation of the solution is sum of these two terms, lattice energy plus hydration energy. Therefore, this is heat of solution is equal to sum of lattice energy and hydration energy. Next, this is positive and this is negative. If the magnitude of the lattice energy is more than hydration energy, the result will become the positive. If lattice energy is greater than hydration energy, the result becomes positive. Lattice energy greater than hydration energy, therefore del H is equal to positive. If del H becomes positive, then we can describe the total dissolution process as endothermic. If lattice energy is less and hydration energy is more, therefore del H becomes negative. Del H becomes negative. If the del H is negative, then we can describe the dissolution process as exothermic. Therefore, whether the heat of solution, that means whether the dissolution process is exothermic or endothermic, will be decided by the relative magnitudes of the lattice energy and hydration energies. Now let us define the definition of the heat of solution. See, the quantity of heat absorbed or liberated during the dissolution of 1 mole of any ionic crystal in such a large quantity of the water is called heat of solution. That means such a large quantity of the water means the quantity of the water should be such a large, further addition of the solvent do not change the heat changes. Next one, heat of neutralization. Heat of neutralization. So this heat of neutralization, it is related to the heat change involved in acid base reaction. For example, HCl is one strong acid, sodium hydroxide is one strong base. If they react with each other, they will produce this salt and H2. So whenever if we conduct the reaction between acid and base, since they have opposite nature, immediately they react with each other, therefore large amount of heat energy will be liberated. Hence heat of neutralization is always negative. It is always negative. Then how to define the quantity of heat liberated during this neutralization reactions? Since it is a chemical reaction, therefore we are defining the quantity of heat liberated with respect to number of equivalents of each reactant participating. Therefore the heat of neutralization is defined as quantity of heat liberated when one equivalent of the acid is neutralized by one equivalent of the base is called heat of neutralization. If strong acid and strong base participates, the quantity of heat liberated is 57.3 kilojoules per equivalent. Or enthalpy change when strong acid and strong base participates is minus 57.3 kilojoules per equivalent. If weak acid or weak base participates, the quantity of heat liberated will be less than this value. So why lesser amount of the heat will be liberated? If either weak acid or weak base participates like this, acetic acid plus NaOH. Acetic acid. Here weak acid and strong base are participating. If either weak acid or weak base is taken like this, if weak acid or weak base participates, since the degree of ionization of the weak acid or weak base is less than 1, therefore only those molecules which have already undergone ionization will participate in the reaction. Hence less number of bonds will be formed, hence less amount of heat energy will be released. Whereas if strong acid and strong base participates, since the degree of ionization is 1, hence all molecules will provide their constituent ions for neutralization reaction, hence more number of bonds will be formed, therefore more amount of heat will be liberated. Next, by observing the difference in the heat liberated from neutralization of strong acid and strong base or from weak acid and strong base, we can calculate the heat of ionization of the weak acid or heat of ionization of the weak base. Therefore heat of ionization of weak acid or weak base is equal to heat of neutralization of weak acid or weak base minus heat of neutralization of strong acid, strong base.